Okay, good afternoon, everyone. Today, we are very happy to have Xiaoxuan Chu from Berkeley National Lab. She's part of the STAR collaboration, and we invited her because she's one of the principal authors of this interesting work of the analysis of di-hadron correlations at RHIC to search for signatures of gluon saturation. So she's going to tell us about this work and also future prospective possibilities at the Electron Ion Collider. So please, Xiaoxuan, go ahead. We are very happy to listen to your seminar.
Thank you, Farrod. So hello, everyone. My name is Xiaoxuan Chu from Berkeley National Lab. So today I'm very happy to give the presentation on proving the nonlinear gluon dynamics at RHIC and the EIC. So this talk will cover the physics topics related to the nonlinear gluon dynamics in PP and PA collisions at RHIC, specifically for STAR. And I will also talk about the related topics in EP and EA collisions, the simulation results at the EIC. And also I will talk about the future opportunities with RHIC STAR. The data is going to be like starting from this year till 2025. So we have more opportunities to study the non-gluon dynamics in the coming 3 years data taken. And the topics is focusing on the studying of the platonic structure of the nucleon or nuclei. So as we know that when the energy increases, the resolution is going to become better. So for example, at a relative low energy, when the resolution is about 10 to minus 14 meters, we could see the nucleus. And if we go to higher energy, the resolution reaches at 1 femtometer, we can see the 3 valence quark inside the nucleon. And if we can go to further high energy and the resolution reaches at 10 to minus 17 meters, we could see more complicated structures inside the nucleon beyond the 3 valence quark. So the big question is, can we understand how the visible matter is formed from the smallest and elementary particles? And in today's talk, so as you can see from this cartoon, you can see take it as a nucleon and there are partons inside. Actually, the parton distributions inside this nucleon can be described into longitudinal direction and also the transverse direction. So for the longitudinal direction, it is defined as the direction of the incoming proton or neutron beam. This is a 1D dimension of the parton distributions, and we call it collinear parton distribution functions. And it is marked with Fx and Q square. And X is represented by the longitudinal momentum fraction of the parton respect to the total momentum of the neutrons. And the Q square is a hard scale. And to measure this collinear parton distribution function is actually one of the most important physics keys for RHIC co-QCD program and the future EIC. So in next slides, I will introduce from the experiment side, how can we extract the information of the collinear parton distribution functions. So this parton distribution function can actually be extracted from different collision systems like the EP collisions and the PP collisions. Here in this slide, I want to take the deep inelastic scattering from EP collisions as an example, since it is a simple and cleaner collisions compared to PP collisions. So in the left side plot, in the EP collisions, the electron behaves as a probe and can be used to study the structure of the target nucleon. And the Q square can be reconstructed through the 4 momentum square transfer from the incoming electron beam to the outgoing electron beam. And you can also take the Q as the transverse resolution. So the transverse resolution is proportional to 1 over Q. With higher Q, we can have a better resolution. So for example, when the Q reaches a high value as 100 GeV, the transfer resolution can be 0.002 femtometer, which is good enough for us to study the platonic structure of the target nucleon. And in the experiment, what we usually do is measuring the differential cross-section of the phyllosite productions. So it is shown in the left term of this formula, and this formula is written in the factorization framework, and which is also the basic concept of the QCD. So the differential cross-section can be factorized into the collinear particle distribution function and the calculable hadronic scattering. And then by using like a global fit, we can extract the collinear particle distribution function by the measuring differential cross-section. So after I introduce this experimental method, I want to show the example results from HIRA measured in EP collisions. In the left plot, it is shown the measured differential cross-section as a function of Q square and X. Basically, the data points can be divided into two groups from the higher X region into the lower X region. So in the high X region, in this region, actually the three valence quark dominate in the EP collisions in the nucleon. And you could see in this high X region, the measured differential cross-section doesn't depend on the Q square. We call this phenomena as a Bjorken scanning. And in this high X region, it's always the leading order DIS process dominate. So it's the exchange, the virtual photon interact with the quark from the nucleon and generates the other quark. If we go to the lower X region, in this region, more and more soft gluons, which carry a low momentum fraction X, emerge. And in this region, we could see a very strong dependence of the measured differential cross-section on Q square. When Q square increases, we could also see the measured cross-section increases. And we call this the Bjorken scanning violated. And actually this violation and this measured cross-section evolution on Q6 square is generated by the gluons. And in this small X region, the gluon-induced process started to play a role in EP collisions. And then I want to show from this measured differential cross-section in X and Q square from HIRA, after we perform this global fit, we can extract the particle distribution functions, the collinear particle distribution function as a function of the momentum fraction X at a fixed Q square is shown in this right plot. And you could see the valence quark density is very high in the high X region. Well, in the low X region, specifically, we usually see X smaller than 0.01 in this region, the gluon dominates. And when we go to smaller and smaller X, the gluon density is actually pretty constrained. So the natural question would be, what is the dynamics of the gluons at this low X regime? And so far, I only show the proton PDF. So in the next slide, I want to show our current knowledge of the nuclear gluon density beyond the proton PDF. So here is our newest nuclear PDF, EPPS 21. So it is showing the nuclear gluon density in the middle and the right plot. The gluon density is presented in two Q square, the lower Q square and the relative high Q square bins. And this extracted gluon density is using the data which is shown in the left-hand side plot. So in this plot, it is S and Q square phase space plot, and we could see the RHIC data basically contribute to the very high Q square regime, and the X covers the range from low value to a high X regime. And for the low Q square to moderate Q square is basically fixed target DAS Drayen and also Phoenix Pi zero results, as well as the D-meson production results. And the small X and small Q square regime we focus on in this analysis. Actually, we don't have much data in this region. And from those data, the extracted gluon density, you could see, especially at a low Q square, the low X regime gluon density is really truly unconstrained. And actually, this small x and small q square region is what the future RHIC data can probe. So we really need this input from the RHIC data to constrain the small x and small q square gluon density. And after I introduce our current knowledge, and then I want to bring up the gluon saturation topic. So the gluon density at the small x and small q square regime is actually a combination of gluon splitting and gluon recombination. So
Xiaoxuan, I have a quick question. So you, in the previous slide, you mentioned upcoming RHIC data. So where would that sit in the plot on the left? Where does the RHIC?
You will see later. I'm going to show
okay.
X and Q square. Yes.
Thank you.
Question. Okay. So the gluon density is actually competitive results between the splitting and recombination. So splitting means the gluon one gluon split into two, and this process generates a power law increase of the gluon density. You could take n as a gluon density, and that's, as I showed before, you could see towards to small x, the gluon density increases rapidly. This linear increase of the gluon density is can be generated by this behavior. And this is the linear dynamics of the gluon density on X. But this growth cannot go forever. So the gluon density has to be tamed at some point. And this slowdown of the growth of the gluon density can be explained by the gluon recombination. So the two gluons can recombine into one, and this process is proportional to n squared. So this is the origin of the nonlinear gluon dynamics coming from. And by adding this nonlinear gluon dynamics term, the total function is a so-called BK evolution equations. And in the X and Q square phase space, the gluon saturation is defined at a point while the gluon splitting and gluon recombination reach a balance between each other. And mathematically, the gluon saturation regime is defined as the Q square smaller than Q square S, and QS is the saturation scale. It is predicted by CGC, the color class condensate framework. QS is proportional to the nuclear mass number A to 1/3, which means in the high value nuclei, the QS is larger, and that makes us easier to access the saturation regime. And from the experiment side, how can we probe these new nuclear gluon distributions at this saturation regime? The di-hadron production is one of the most direct and sensitive channels to probe the saturation. It was first proposed by Dima Kazev and his collaborators in 2005. So it is proposed that we can measure the two particle correlations in PP collisions and PA or DA collisions. For PP collisions, it is a baseline study with a typical 2-to-2 process. So the two partons interact with each other and generates back-to-back digest or two high PD particles in 5 directions. And this gives us the two particles correlation, and which peaks at delta phi equals to pi. So this is a correlation for PP collisions. And for PA or DA collisions, since for the nuclei beam, there is a gluon saturation involved, and that will generate this suppression of the back-to-back correlations in D-gold collisions compared to PP. And this suppression of this back-to-back correlation is taken as a saturation signature. So after they propose this idea, there are more detailed predictions on this suppression feature for saturation physics. As I mentioned before, we want to access the small x and the small q square regime. And in this cartoon, it tells us, actually in these PA collisions, we want to select the very asymmetric collisions. We want to select the high X quark interacting with the low X gluon from the nuclear side, this kind of process. And the kinematics of X2, target X2, and the Q square, Q, can be reconstructed from the outgoing two particles kinematics of PT and rapidity. So you could see X2 is proportional to PT and anti-proportional to rapidity, and Q is proportional to PT because it's basically the average PT of those two detected particles. So basically, if we want to go to small x and small q square events, we would like to detect lower PT particles and more forward particles. And these signatures are described detailed in these two plots. In the middle, in the left side plot, by varying the PT, you could see from 3 GeV high PT to low PT 1.5 GeV, you could see a very strong suppression by detecting lower PT particles. And in the right-hand side, you could see by detecting more forward particles, rapidity from 1.5 to 3, and we could see stronger suppression in forward detections. And you could also see the signature is more sensitive to PT than the rapidity. This is one aspect by varying the kinematics of the detected two particles. And the other aspect is by varying the QS, so the saturation scale. The saturation scale is predicted to be anti-proportional to the impact parameter B and proportional to the mass number A, as I previously mentioned. So by probing the collisions, more central collisions compared to the peripheral collisions, we could see more suppression in the central collision. And from proton to gold with a high value nuclei, when the mass increases, QS increases, that is also can help us to access the small x, the saturation regime. So next question will be, from our experiment side, can we really see these detailed signatures of gluon saturation? So I want to introduce the RHIC data of PP, PA, and DA collisions. And a little bit introduction of the experimental setup. So we measure the two forward pi zero correlations in 4 collision systems, PP, P aluminum, P gold, and D gold collisions at 200 GeV. And the two forward pi zeros are reconstructed through this forward detector FMS. The rapidity coverage is 2.6 to 4. And then we can compare the measured back-to-back correlations in these 4 collision systems. Besides that, we also measure the event activity dependence. The event activity is actually defined as the energy deposited in the nuclei going directions. So for example, in P gold collision, we group our events into different event activity. High energy deposition represents high event activity. High activity also corresponds to a more central collision. Event activity is not identical as a traditional definition of the centrality, but it also describes the degree of the violence of the collision. So that's another point for our measurement. Before I directly show the results, I want to answer.
Can I ask you one more question? Oh, yeah. Sorry, I have another question.
Yeah, sure.
So if I recall correctly, the connection between multiplicity and impact parameter is usually done by some kind of Glauber model, right? Is there something similar that allows you to have a quantitative correspondence between event activity?
For PA is very difficult, very challenging to perform the global fit. So you can also see the publications from RHIC of that P-light. They just overlap with each other. So it's not like AA collisions. They are one-to-one corresponding to each other, the impact parameter B and the multiplicity. So it's very complicated for PA collisions. And so now this event activity is the best we can do. But I think furthermore, from the theoretic side, we should also think about for PA collisions, these small system collisions, what is the best observable that can be correlated with the impact parameter E.
Right. Yes. Yeah. Okay.
Yeah. Okay. So here is the phase space. This curve represents the saturation scale in terms of the gold beam, and the rapidity equals to 4 represents the most forward direction we can detect for the ferrous particles, and that corresponds to the smallest x we can probe. And this is a boundary between perturbative and non-perturbative regime. So actually, RHIC data can probe the non-saturation regime transfer into the saturation regime. So that is our data, where our data come from. And then finally comes to our data. So first I want to show the PT and mass number 8 dependence of the back-to-back correlations for these two pi zeros. So in the left side plot, this is two pi zero correlations in 3 collision system. The blue one is the PP collisions, black is the P aluminum collisions, and red is the P gold collisions. And the upper panel represents a lower PT range that corresponds to a lower X and a lower Q square regime. And we could see clearly the suppression, that is the strong suppression in PA collisions compared to PP collisions, and there is a larger suppression in P gold compared to P aluminum collisions. In the bottom panel, that corresponds to a higher PT regime. Higher PT represents high X and high Q square, which means it is far away from the saturation regime. And we see the measured back-to-back correlation are on top of each other for the 3 collision systems. And then we want to quantitatively study this saturation amount. So we perform a Gaussian fit for all of the correlation functions in 3 collision systems. According to the fit, we can extract the area of the correlation function for each collision system and also the width. So by comparing the area, for example, the area in PA divided by the area in PP collisions, if this area ratio is smaller than 1, of course, that means we see the suppression. So that generates the right-hand side plot. This is the area ratio of PA over PP. So for PP, it's PP divided by PV. So it's a baseline equals to 1. And the second point is the area in P aluminum collisions compared to PP collisions. We see basically 20 to 30% of the suppression in P aluminum compared to PP collisions. And for P gold, we see more suppression, is about 40% suppression in P gold collision compared to PP collisions. And we also observe the linear dependence of the suppression amount on the nuclear mass number 8 to 1/3. And I think the extracted slope minus 0.1 would be very important input for the saturation model in CGC framework. So this is a PT dependence and A dependence we observed from star data. And next page, I want to show the event activity dependence. So
sorry, can I ask you one more question? I see.
I also have a question.
Yep, go ahead, Fen.
Yeah. So I remember asking you and Elka about this whole phi distribution. Do you have that plot too?
We have that plot. The near side peak, we didn't show that is for FMS. We reconstructed pi zero from 2 decayed photons. So the near side means the 2 photons can kind of overlap with each other because they are very close in phi and eta. And the FMS currently doesn't have the capability to really distinguish the overlap pi zero or photons. So if we present this near side peak in the paper, I think that will require another analysis for that to estimate the systematic uncertainty from the detector effect. And currently, if we do not include that study, the near side peak is on top of each other for the 3 collision system. That's our results, but that needs a full analysis to estimate the systematic effect.
So you mentioned that you did a Gaussian fit for this distribution, right? Do you have curve for that? So my question that, for example, how in particular, for example, for phi equal to half pi or close to half pi, your PP, PA are so different, right? So if you have curve, do you have curve for that?
Yes, I think I do. And yeah, you mean you want to see the difference at this point, right? About the fitting.
Yes.
And you expect them to be in which?
So in your fit, you will be the same because it's Gaussian fit, right? And you're away from phi equal to pi, so then Gaussian just decrease all the curve into the same. but your data actually have so big difference. For example, at delta phi equal to half pi or close like 2, right? So what I mean is that if you do a Gaussian fade, I believe you will get something similar the Gaussian width, but you cannot really explain that. For example, at delta phi away from the pi, so that means they're not in the back-to-back correlation kinematics. Your data show big difference. If you fade just with simple Gaussian, they will just collapse to the single point. So it would be nice to see this comparison with your Gaussian fade, actually. So you will know the physics much better. You see my point?
We tried different fitting range, not just ends at half pi. We tried the whole range of the fitting. So it gives us the same results, actually.
No. If you just do a single Gaussian fade, like you say, if you have curve, that will be very clear. You know the Gaussian will decrease dramatically, exponentially, right? That's how the Gaussian fade means, right? So it will decrease exponentially. So that means when you away from the back-to-back, like delta phi equal to 2, and go to half pi, all the Gaussian fade, all the 3 curves will collapse into almost one point if you plot linearly. I mean, if you plot on logarithmic scale, of course, you can still see the difference. But your data clearly show the significant difference compared PP and PA, even at the delta phi is away from delta pi, delta phi away from the pi. You see my point?
Yeah, understand.
I see.
So you'll
has a comment maybe.
So it will be very nice to have this curve comparison, because the interpretation of your data really depends on how you do the fit, right?
Yes.
Ernst, do you want to make a comment about Feng's?
Yeah, it is closely related, actually. So Feng, I think I totally understand your comment about that in the ideal case, you would want to see a full description of the entire spectrum, right?
Yes.
So including the near side and including the away side. Now, that is not what is here, right? So what Xiaoxuan is presenting. But what I actually don't understand in your comment is why be, well, let me call it hung up on a Gaussian shape. It's not obvious to me that this shape has to be Gaussian. I mean, I totally understand that one would like to, let's say, have a full description of the spectrum, but I don't think that there's anything fundamental about a Gaussian here. So in other words, I am not so sure what to read into a difference, let's say, near an angle that is maybe pi divided by 2, right? I mean, there's some scatter going on there. If I just compare in the top figure, let's say the black points, right? I mean, that clearly is, that has a structure that goes beyond what is shown as the statistical uncertainties, maybe. Right, and likewise, I mean, I tend to see this elsewhere too. So I think I totally appreciate your point. I'm not sure that I think that a Gaussian curve would solve this or even address it. But I'm happy to be, I mean, if you have a good argument the other way, then I'm happy to learn, right?
Yeah. So let me finish my comment. So if you are around the delta phi equal to pi, it's back-to-back region, right? The Gaussian fade does make sense, right? And if you are way away, it's like delta phi equal to half pi. So physics-wise, the PPPA, whatever different A's should be the same. So the same physics contributing to delta phi equal to half pi, for example. So I would imagine, I mean, I'm serious, okay? So I would imagine from a theoretical point of view that in that region, for example, delta phi equal to half pi, all the curves should be the same because there's no other physics going on.
I have a comment about this. So what about
so the underlying physics? Why is the data different? Because the underlying physics is not clear in this kinematics. Why you have huge contribution from so-called pedestal?
Yeah, exactly.
Because if you plot the whole delta phi distribution, you can clearly see the baseline for PP and PA are so different, right? I mean, although Xiaoxuan mentioned that the near side they are almost the same, but because the near side is such a big peak, you cannot really see the small difference when you compare to the baseline. So in the sense that the baseline for this PPPA for this analysis, either the theoretic understanding is not complete, so there's a huge theoretic uncertainty for that, or there is a systematic uncertainty that experiment cannot account for. So for example, if you subtract the pedestal whatever contribution, the whole distribution will be totally different.
So that
I firmly believe, let me finish. I firmly believe your data already shows the PD broadly effect if you subtract the pedestal contribution.
I did subtract the pedestal.
And then the interpretation of your suppression effect of the right plot will be strongly modified.
So all of these area and width are actually performed after subtract the pedestal. It's already performed. The area we extract for this plot and the following plot for the broadening like the width is already performed after pedestal extracted. Of course, we should take out the background like correlations. That's
why I ask you to have the curve comparison with the data point.
Yeah, so Feng, I don't think that one can just upfront impose that nature should tell us that there is a very clearly separated near side and away side, and therefore that the system needs to be identical at half pi. Okay, I mean, it's not, I mean, the way I look at it is it's not up to us to say that, it's whatever we observe.
Yeah, of course.
I mean, I understand, let's say, if you go into interpretation,
no,
but
yes, that's my point. You have to have clear interpretation of that. I mean, of course, the measurement is
experimentalists.
Wait a second. Okay, so experiment, you also have to, for example, like Xiaoxuan mentioned that in all the study, you have already taken into account the pedestal, right? But how you take into account the pedestal? I mean, that's your way to interpret the data. I mean, if you just give me raw data, right? You don't do any additional analysis, then that's I'm completely fine. But you already did something, right, on top of that. So I have a simple question. Why delta phi, for example, here equal to half pi, they have significant difference between PP, PA, and case. If you're telling me that there's a physics behind that, I'm happy to hear.
You mean here is different?
Yeah.
I think the slightly pedestal, my opinion would be in PA collisions. I will also mention in the later, that would be a chance of the double part interactions. So the pi zeros can be not just two pi zeros, not just from the one single part scattering, it can be double part scattering. It could be different in PP, P aluminum, and P gold. But overall, this after we perform this Gaussian feed and extract the pedestal, we also combine our pedestal. The pedestal with the systematic uncertainty, actually we cannot tell. It's dramatically different from PP and P gold. That is the data tells us.
So I think
so that's why.
Sorry,
okay.
We're dwelling on this point too much. This is very important, of course. This is one of the central slides, I believe, of Xiaoxuan's work, but maybe let's move on and we can come back. I also have a few questions about the pedestal, but for the sake of time, let's move on.
Yeah, sure.
Oh yeah, sure.
Okay, so apart from this PT and A dependence, we also study the event activity dependence, which can be shown in the left-hand side plot. So we are plotting this area ratio as a function of the event activity for P gold and P aluminum collisions. For both of the collisions, we see the same trend that the higher event activity reflect the larger suppression in both P gold and P aluminum collisions. And since for P gold, we have enough statistic, so we divide this highest event activity beam and the lowest event activity beams into different PT, and that generates the right-hand side plot. The black markers represent the lowest event activity data, and the red one represents the highest event activity data. The main point of this figure is we compare our data with the prediction of the CGC according to running constant BK model. And it is not an apple-to-apple comparison. The highest event activity is compared to the most central collision with the impact parameter B equals to 0. And we see agreement between the data and the predictions. And the last one is, as we discussed about the broadening. So the extracted width of PP and P gold and PP is actually, the ratio is very close to 1. So we didn't observe the broadening in P gold collisions compared to PP. And those are all the data from the PP and PA collisions. And then I want to—
Excuse me, Xiaoxuan, Feng has a question.
Okay.
No, just a comment. So Xiaoxuan, so if you say something agree with the prediction, you have to basically compare to all the distribution, all the data, right? As far as I know, all CGC calculation predict the PD broadening. So you cannot say just the relative area agree with one calculation with CGC. So in the sense, it's a contradiction with each other. So yeah, for example, your curve, your RCBK curve there, they also have delta phi curve, which doesn't agree with your data. So I think when you mention about something, you have to be careful about this.
That's true. And the reason we didn't put the width inside is the author of this prediction. They didn't include the gluon, soft gluon radiation, so they ask us to not use the width. So we also want to be safe with that. And like you said, yes, the broadening is not observed.
So no. That's also a false statement. So if they include the soft gluon radiation, that's Sudakov. That's already in our calculation, which is sent to you. The Sudakov doesn't contribute, doesn't actually modify the PD broadening effects. So if they say that, they just hide their prediction. So you say what I mean. So you have to get the physics correct. I mean, you cannot take their argument just to say they say something that doesn't give you any additional prediction. But the Sudakov doesn't really change the PD broadening prediction from CGC, period.
If the width they predict is not a correct number, I don't think it is correct to use them in to compare with the data. But I agree that for the broadening phenomena, yes, it is a lot as the CGC predicted, and which is clearly mentioned here. We are not hiding like any information, so we didn't observe the broadening.
Sorry, Feng, what do you mean that the Sudakov, what is the effect of the Sudakov then in this case, if it's not the broadening? Maybe you can be a little bit more precise. Yeah.
So what the Xiaoxuan show here is from Tom's Lapis calculation, right? Or somebody else's calculation.
Cyril Marquette, right?
Yeah, I don't know. There's definitely some calculation which give you this suppression, right? And but all this suppression prediction from CGC also predict this will be PD broadening. And the reason why Xiaoxuan didn't compare that with their data is that in the delta phi distribution, there's no contribution from soft gluon radiation. That's just Sudakov effect.
Yes.
But we know that pseudo effect doesn't affect the Peter Brodin phenomena or effect in the file distribution in this kinematic region for the star data. We have shown that. So there's no comparison for the file distribution. The reason was given is not correct. So it's just misleading in the sense.
Sorry, maybe you should defer this discussion for later, but just a very quick question. So you're saying that the pseudocov doesn't have any strong effect because the PTs are small, or?
Yes.
Okay.
Yes. In this kinematics.
Okay, and you are referring to your work with Anna and Bowen. Is that?
Yeah, we had that. Also, we also later had the PA prediction later on. So yeah, in Anna's paper, we already have pseudocov effects there.
But
Okay.
as we discussed before, there is a normalization issue in PP. So you only have PA, there is no PP.
Yeah, that's true.
Yeah, that's why we didn't use the predictions from that part, because the main point is to compare PP and PA. If there is no available PP, so it's not like comprehensive to only put PP on set on it.
I understand that, but I'm just saying that, so the physics has to be consistent. When you talk about CGC or saturation comparison, you have to take the whole comparison. You don't want to just show something which agree with CGC calculation, something actually doesn't agree with CGC. You should have both of them, right?
Okay, I understand the point.
In other words, you say if your data already show evidence for the gluon saturation or nonlinear effects for the saturation or CGC prediction, CGC also predicted Peter Brodin, which you didn't say, right? So you have to, the message has to be consistent. That's my major concern about here.
Okay, thanks for your suggestion. Okay, then I want to talk about the results we have, the new results we have for d-gold. Actually, d-gold has been measured before, like more than 10 years ago from Phoenix experiment. And the reason we want to revisit this measurement at STAR is from the series, they pointed out that there would be a possibility of the double part interactions. So here in the left cartoon, it is a single part interactions and produce two pions from these single part interactions. And in the right side is a double part interactions. So the two pi zeros can come from the different hard scattering. And the question would be, how can we address these double part interaction contributions to d-gold or PA collisions? And as a fact that if there are two hard scattering, let's say A and A prime or B and B prime, they are not correlated. So they're generated two pi zeros would also not correlated, and that would not affect the measured correlations we are using as STAR data. But if from the initial state, A and A prime or B and B prime, they are correlated. So these two produced pi zeros can be correlated, and this correlation can be a background correlations as what we want measured from this physics. The good thing is it is predicted that the double part interactions behaves differently in PP, PA, and DA collisions. So for example, in PP collisions, the double part interactions can only happen that these two partons, they are incoming partons, they come from the same nucleon and interact the nucleon like the other proton beam and produce two pi zeros. And for PA collisions, apart from this #1 procedure, we can also have this additional contribution that these two partons coming from the proton, but individually interacting with a different nucleon from the gold beam. And for d-gold, apart from the previous two items, it has also the additional contribution from this. So the two partons coming from the different nucleon and interact from different nucleon of the gold beam. So ideally, if we can measure the two forward particle correlations in the three collision system and we compare them one by one, so that can really make it possible for us to study the sample process contribution in terms of the double part interactions one by one. So let's see our results. This is the first left side plot is the pi-zero environment mass distribution for PP, P gold, and D gold collisions. And we selected a mass window, the unmasked window, for this pi-zero candidate selection. And we noticed that for D gold, the background is super large compared to the PP and PA collisions. For PP and PA, they are very close with each other, but for D gold, the background is very large. From the selected unmasked window correlations, we can see from the right-hand side plot in the left panel. So the correlation is for the three collision system is directly compared with each other. For PP and P gold, that is exactly as I showed in the previous slides. And for D gold, you can see the pedestal is super high in D gold collisions compared to PP. And if we do a subtraction of the pedestal to move the D gold correlations shifted into the same pedestal as in P gold, we see actually in D gold there is no suppression in D gold compared to PP collisions. And we also compare our results of the previous published Phoenix result. So it is not an apple-to-apple comparison, it's only a quantitative comparison between STAR and Phoenix results. So for STAR, there are different experiment setup. For STAR, we measure two pi-zero correlations in the rapidity range of 2.6 to 4. For Phoenix, they are measuring the cluster and pi-zero correlations in slightly different rapidity range from 3 to 3.8. And the area ratio of D gold over PP is plotted as a function of event activity at STAR and as a function of number of Ballerinic collisions at Phoenix. So if we want to make just a qualitative comparison, we can choose overlap PT range of two experiments. The associated PT particle, the associated PT is the same between 1 to 1.5 between the two experiments, and we can compare actually the overlapping PT range. Let's see the STAR markers from the Phoenix and also the STAR markers from the STAR. The PT is slightly different, but the overlapping range is very large. So we can see for both of the experiment, the area ratio of D gold over PP, STAR is even higher than 1, and for Phoenix is close to 1. And as just show the example results of Phoenix. So this is the direct comparison of the correlation function in D gold and PP after pedestal subtracted. So you could see the back-to-back correlation, the central collision D gold and the PP collisions, the back-to-back correlations are almost on top of each other. So in the overlapping PT range at both STAR and Phoenix, we didn't observe the suppression. And the reason why this ratio is still higher than in STAR and Phoenix is the background signal and over background ratio is different compared to two experiments. But the conclusion is in this overlapping PT range, for both of the collaborations, we didn't observe the suppression, and there is no event activity dependence nor centrality dependence for STAR and Phoenix. So for this pi-zero measurement, one thing is the background in D gold is too high compared to PP and PA. The other thing is double particle interactions is undetermined, and that makes the D gold measurements very challenging. So actually, this pi-zero measurement favors cleaner PA collisions compared to D gold collisions. The good news is we will have more PA data in 2024 with STAR forward upgrade. So the forward upgrade consists of 3 new subsystems: the forward silicon tracker, forward STGC, and forward collimeter system. And we will have more PP and PA data in 2024. And those data with the forward upgrade will enable us to explore the nonlinear gluon dynamics further with expanded observables. So with the tracking benefit of the tracking system, we can measure the di-charge hadron correlations beyond the neutron pi-zero correlations. And because of the high resolution of the tracking system, we can access very low PT. So the minimal PT of the previous collimeter FMS is 1 GeV. Now we can probe down to 0.2 GeV. And then beyond the particle correlations, we can also measure di-jet correlations and direct photon measurement. So we have some projection study for direct photon measurement. This channel is a gluon complex scattering. It is very sensitive to the gluon dynamics, and the direct photon can also help us to remove the fellow state effect. The challenge would be the cross-section of the direct photon measurement would be very small, and it is very difficult to extract the background photons. And here is by adding the projected data from the 2024 one, and actually for both of the models, the SSZ and EPS09, the nuclear modification factor can be, the uncertainty can be reduced significantly by adding the projected data in the future. And I also want to mention the simulation studies for di-jet measurement. So in the top plot, this is the simulated X2 range. This is our target site X, and also then compared with the X distribution from the di-jet. So from our study, the di-pi 0 at 200 GeV collisions, the X actually covers a wide range from very low value to a large value. So we do have some contamination of the large X events in the selected collisions. And di-jet, the advantage of the di-jet would be the di-jet can help us to select cleaner small X2 channels. So you could see the X2 basically dominated at a very low X region, and the jets are more current proxy to the parton level. But the disadvantage would be the jet, usually the jet minimum PT at start is 5 GeV. So the PT can be a little bit too high and push the data to a high Q-square event. And this is what I want to introduce the results from Atlas. So they were measuring the di-jet correlations, and the area ratio of P-light over PP is plotted as a function of the rapidity. So in the backward and the middle rapidity, they didn't observe any suppression, and for the most forward direction, they see like 20%, around 20% of the suppression. So the question is, the energy is very, very high at Atlas, so that can push the data to a very low X, down to 10 to minus 4, dominated at this region. But since the PT is too high for the jet, so the Q square is greater or equal to 800 GeV. So that could be the reason why the Atlas di-jet data doesn't observe the strong suppression as what we observed at start. And for the weights extracted as a sigma from the Gaussian fate, so they remain the same, the ratio between P-light and PP. So for this side, the conclusion is the same as the RHIC di-hadron correlations measurement. Apart from the future opportunities with the sub-4 upgrade RHIC PP and PA data, I also want to see our plan for the channels in the UPC. So it is gold-gold collisions, but actually it's the nature of the collision is the exchange photon interact with the gold. And from the cartoon, you could see we want to study the jet and the di-jet production in these UPC events, and that would be very deeply connected to the future EIC measurement, because it's actually the same procedure but with a different kinematics. So the incoming photon can be either provided by the electron beam, and for the UPC, it could be provided by the gold beam. So this is also a part of our future plan to investigate the partonic structure inside the nuclei. And then I want to mention the future measurement at the future EIC. So this is a simulation study. So we simulate the EP and EA collisions, and we measure the back-to-back correlations in EP and EA. So here is with the saturation model implemented in EA collisions, we could see the signature of the suppression in back-to-back correlations in EA collisions compared to EP collisions. And if we do not include this saturation model, and you could not see this suppression. So that means the EIC has the capability to do the similar measurements, dihadron measurements at EIC to probe the saturation physics. And actually from this paper, it is detailed studied by different factors which can influence the correlation shape. So the intrinsic KT, initial state radiation, final state radiation, and the fragment PT. And each of them, you could see the near sideways is mainly affected by the final state effect, final state partial shower and fragment PT. But away side is dominated, influenced by the initial partial shower. So at EIC, I think by measuring the die-charged hadron correlations, we can study their contributions by individual impact. And the last measurement I want to mention is beyond these dihadron correlations, we can also measure the diffractive at EIC. So the diffractive GFSI productions, and we can measure, it is predicted, like we can measure the double ratios of the diffractive over the total cross sections in EA collisions compared to EP collisions. The double ratio is predicted to be higher with the saturation model and higher than 1, and it is predicted to be lower than 1 with the shadowing model. I think this would be a very good chance for us to really separate the effect from shadowing and saturation. And then I want to see the connection between all of the measurements between the different colliders. So as I showed before, this is the RHIC. Actually, RHIC data can actually probe the to some extent similar X and Q square phase space as the EIC. And for the RHIC, they probe different X and Q square. So by combining all the data from different colliders, we can really know the global results, like in different phase space. And by compare EIC, EA collisions to PA collisions, so the nonlinear effects seen at the different complementary probes, if we can observe that in different collision systems, one can claim the discovery of the saturation effect and their universality. And then that comes to my summary. So this talk, we focuses on the gluon distributions inside the nucleon or nuclei. So I showed the current results of the two particle correlations in PP and PA collisions at RHIC. So we observe the A dependence, the event activity, or centrality dependence, and PT dependence. Also the rapidity dependence as predicted in CGC. And then I also talk about the revisited measurement in D-gold collisions, but we have some challenges here for D-gold collisions. And for the outlook, after all of the data implemented and to extract the nuclear PDF, there's 3 groups actually gives us very different nuclear gluon densities at small x. So here, for this region, small x region, we still need a lot of experimental input to really help us to constrain the nuclear dynamics at this region. And I talk about the possibility with star forward upgrade and the UPC channels at RHIC, and also the 2 jets production at the RHIC and the future measurement and EIC in the EP and EA collisions. And by combine all of the data, we can really study the complementary and the universality and factorization. So that's all from my side. Thank you.
Thank you very much, Xiaoxuan, for this comprehensive talk discussing many potential observables for gluon saturation. Let me clap on behalf of the audience for your nice seminar. Let's open the room for some questions. So I see Spencer, please go ahead.
Thanks. Can you go back? You had a slide comparing the X values for dihadrons and dijets. Go back.
Oh, sorry.
Yeah, that one.
Fast.
Yeah. So I don't understand how the dijets can get down to such low X values. And also more generally, how they can be at lower X values than the dipions. I mean, if you take if you have a parton with x times 10 to the minus fifth hitting a parton with an x of 1, that doesn't seem to me to give you enough energy to produce jets with PT above 5 GeV over C. So maybe I'm missing, can you give me sort of an example of that kinematics?
Kinematics.
And or explain how the dijets get to lower X values than the dihadron.
So first of all, the collision energy is quite high. It's not 200 GeV, it's 500 GeV. So it's a bit different.
Okay.
So that makes really the X push
okay.
to a lower value.
Okay.
I think that is the main reason. I also checked that. So sorry, I didn't make it clear because I just want to show the advantage and disadvantage of actual measurement, and actually the collision energy is different.
Okay, that would be a factor. I still don't see how you get to such low X values. Because basically you have a 250 GeV parton hitting essentially a 25 MeV, a 25 MeV parton, or and doesn't seem like there's enough energy there.
Yeah, the energy could be the 4 times 25 MeV times 25 GeV, and take the square root of that. I cannot get the number. No. I will definitely have a look. Yeah.
Okay.
Right. So isn't the pocket formula for this kind of thing like x1 times x2 times the center of mass energy square is roughly PT square? Is
Yeah,
that
yeah, right. Exactly.
right? So can we have an estimate from that? So let's say the blue region, let's say is 10 to the minus 4.
Or yeah.
Then red is like 1. So x1 times x2, that's 10 to the minus 4 times 500 square. Sorry, I'm a bit slow with the math. So that's what is it? 25. So that's like roughly, it is consistent, right? So 10 to the minus 4
right?
times 500 square, that's
Yeah,
about
but
25.
Goes down to 10 to the minus 5 here.
Yeah. Fair enough. Maybe that's yeah, because here it's the PTs are, 10 to the minus 4 sounds reasonable to me. 10 to the minus 5, maybe it's a bit too small.
10 to the minus 5 would be 10, right? Then the PT square.
Yeah, maybe it's worth having a look at that archive reference.
Yeah, I think
To
it's
see
the
what
minimum
they
PT maybe is a 3 GeV.
Okay, thanks, Spencer. Do we have any further questions for Xiaoxuan? I'm sure Fong has some additional comments, but does anybody have any additional input? Okay, so we already have many questions during your seminar. So let's formally close your presentation today. Thank you again very much.
Thank you.
Thanks for staying with us. And maybe those of you, if you want to have any further discussion with Xiaoxuan, we can stay a little bit longer. But let me formally stop the recording.